We're going to take a look at some real life graphs and focus in on questions you might get in an exam in relation to real life graphs. So we'll be looking at speed, distance, time graphs and conversion graphs and things like that. So let's take a little look at some of the questions you could potentially get. So these are all questions of past exams. So Rebecca went on a bike ride. The graph shows Rebecca's distance from home on her bike ride. So along the bottom of the graph you have the time, and up the side you have her distance from home. So this first line on the graph, you can see here from 0 up to this point. This is where she is travelling away from home, and as the time increases, so does her distance from home. Then you get a little horizontal line along the top, and that means that her distance hasn't changed. She's still at 12 kilometres from home, so at that point she's actually stopped. She's in the same place. And then from the top down to the bottom, this is where she's returning back to her home. So as the time continues to increase, she gets closer back to being at 0 kilometres from her home. So the first question there says A, how far had Rebecca travelled after 30 minutes? So her time's along the bottom, so there's our 30 minutes. So what we do from there is we will draw a line up to our graph, and probably the best thing you can do here is to use a ruler. So up to where we meet the line of the graph, and then we go across and read off from there, and that says that at 30 minutes she was actually 6 kilometres from home. Our second question then says, after 60 minutes, Rebecca stopped for a rest. And we've already discussed that that rest is this straight line at the top. It says, for how many minutes did she rest? So the start of her rest was here at 60 minutes. Her rest ended then here. So we need to work out what each of these intervals is. So for 3 spaces, 1, 2, 3, you have 30 minutes. So 30 divided by 3 means each little space is 10 minutes. So that would be 60, 70, 80. So she's actually spent 10, 20 minutes resting. Now the last part says, see, how far did Rebecca travel in total? So we know that in the first part she went from 0 to 12. So she went from 0 to 12 kilometres from home. And then after a rest, she went from 12 back down to 0. So that means she has travelled 12 kilometres away from her home, and then another 12 kilometres to getting back home. So in total, she's actually travelled 24 kilometres. Right, let's have a look at another question then. So Emily drove to the beach. She stayed at the beach and then drove back home. Here is Emily's graph. So again, the same kind of idea as our last question. Now, you could pause the video at this point and maybe try and answer some of these yourself. Otherwise, just work along with me. So it says here, for how many minutes did Emily stay at the beach? So we have the first part of her journey here. So she's 0 miles from home. Then she travels up to this point, which she is now 35 miles from home. Then the distance doesn't change. It's staying at 35 to this point. So this is the number of minutes she's actually stayed at the beach. She hasn't moved anywhere. She hasn't gone any further from home or any closer to home. So we want to find out how long that is. So if we draw a line down, again, it'd be better using a ruler for this, to there. And then again from here down. Oh, my line's gone off a wee bit. But from that you can see, so it's halfway between 1430 and 1500 hours, so that would be 1445, and the other line comes down at exactly 1600 hours. So we want to find out how many minutes that is. Well, from 1445 to 1500 hours, that is 15 minutes, and then from 15 to 1600 hours is an hour. So an hour is actually 60 minutes. So 15 plus 60 means that she's at the beach for 75 minutes in total. Now part B says, what was Emily's average speed on her journey to the beach? Now for that we need to know this little equation, that speed is equal to distance divided by time. So there's 2 pieces of information we need to know here, and we need to know her distance. So it says, what was Emily's average speed on her journey to the beach? So her journey to the beach, the distance of that journey is here, so that's 35, and that's 35 miles, so 35 miles. And we're going to divide that by the time it took her to make that journey. So if we go across and down, which we've already done so far, that has taken her 30 minutes plus another 15 minutes, so a total of 45 minutes. Now the problem with that is 45 minutes, speed isn't measured normally in miles per minute, and as you can see from the answer here, it's actually miles per hour. So instead of using 45 minutes, we need to change that into hours. Now 45 minutes is 3/4 of an hour, and 3/4 as a decimal is 0.75. So we're just going to put 0.75 in here. So we're going to have to do 35 divided by 0.75, and that's something you would probably want to use your calculator for. So if you take out your calculator and work out 35 and divide that by 0.75, and it comes up as 46.6 recurring. So that is 46 point, and if you round that to one decimal place, that'll be 46.7 miles per hour. So Emily was doing an average speed of 46.7 miles per hour, or you could round that even to the nearest whole number of 47 miles per hour. Alright, so let's take a look at another question you could get here. And now we've moved into a different type of graph here, and it says Bill is a taxi driver. You can use this graph to find the cost of a taxi for different distances. So we're using this graph, if we know the distance, then we can work out the cost of the taxi journey. For each journey, there is a fixed charge. Okay, so we can see that even if you go 0 miles, there's actually going to be a charge. So that's your fixed charge. And it's asking us then, how much is this fixed charge? So that's exactly halfway between 0 and 10. So that means that the fixed charge would be £5. Now Bill makes 2 journeys. The distance of one journey is 10 miles further than the other journey. Work out the difference between the 2 journey costs. Okay, so let's say one of his journeys is 10 miles. And because there's a 10-mile difference, so the other one then would be 20 miles. Now if we work out how much it would cost him if he went 10 miles, so if you draw up to where you meet the line on the graph and then draw across, that works out at, if that line was straight, that works at £20. And if he was to go 20 miles, that's 10 miles further. Then you go to your 20, again use a ruler if you can to draw these onto your test paper. And you go up to the line, and then you go across to where you meet the cost, and that comes out exactly between 30 and 40, so that's actually £35. So difference means we're going to take away, so 35 take away 20 will give you a £15 difference. So there's a £15 difference if there's 10 miles between the 2 distances of the journeys. Now you could do that against 2 other points in the graph. You could say, for example, what if one of his journeys was 0 miles, and that works out at £5. So if you look at 0 miles there, it comes up to £5. And then 10 miles further, well, go back to your 10, we've already done that. That's actually working out at £20. So the difference between 20 and 5, so 20 by 5 is 15. So regardless of which 2 distances you take, you're still going to get a difference of £15. Okay, let's look at another graph here with a straight line. So John draws a graph to show the amount of petrol his car used on a 250-mile journey. And then we go down here and it says how much petrol was in John's car at the start of his journey. So at the start of his journey, he would have travelled a distance of 0 miles. So we want to work out how much petrol he had in his car at this point. So if we go up to where our line is, and that's up here, and that's sitting exactly between 40 and 50. So that means he's actually got 45 litres of petrol in his car before he actually moves any distance. Now in B then it says how many more miles can John's car travel before it runs out of petrol. So you can see here he's at 250 miles. Okay, so we're wanting to see when he hasn't run out yet, he's still 10 litres of petrol. So we need to work out then how far another 10 litres of petrol will actually take him. So let's say here we have another 10 litres of petrol. So if we work out how much actual distance he covered in the last 10 litres of petrol, then we can work out how much further he can go over his 250 miles. So let's zoom in on our graph here a little bit just so we can get a clearer look. So at 10 litres of petrol, okay, that's working out at 250 miles. So 10 litres of petrol is bringing us to 250 miles. And then if we go to 20, and if we draw across at 20, meets the line just there. We want to be nice and accurate. And if we draw down, so that's 150, 160, 170, 180, 190, 200. So we're actually not going up in tens, we're going up in fives. So 150, 155, 160, 165, 170, 175, 180. So at 20 litres, he was at 180 miles. So that means in that 10 litres of petrol, he was able to cover, if we work out the difference between those two, so 0 minus 0 is 0, 8 away from 5 you can't do, so we'll stroke that out. And we're now doing 8 away from 15, so that's 7, and 1 away from 1 is 0. So actually, with 10 litres of petrol, he is able to cover 70 miles. Okay, so it says, how many more miles can John's car travel before it runs out of petrol? So according to the graph, he can do another 70 miles before he is going to run out of petrol. So this graph only takes us up to 250 miles, but another additional 70 miles will be travelled before he's actually going to run out of petrol. And it says then, C, what assumption have you made to calculate your answer to B? Well, we have assumed that the graph is going to stay at that steady angle, that steady line, that he isn't going to start using more petrol, because if you know anything about cars, you know the faster you go, the more petrol you use, and things like that. So also he could at this point fill up the car and things like that. So those are the assumptions that we're making, that he's going to stay at a steady speed and that the consumption or the rate at which he's using his petrol will stay exactly the same. Okay, so we've got a conversion graph here, and it says the conversion graph can be used to change from pounds into euros. So you can change from pounds to euros or euros to pounds. And it says use the graph to change 30 pounds to euros. So we want to be quite accurate with this. So again, we're going to zoom in and we're going to find our 30 pounds. So here's our pound side. So you need to go to the correct side at this time. So there's our pounds, or 30 pounds. We're going to follow that line up from 30. And again, if you've got a ruler, use a ruler, so that you get this straight and you don't do a wobble like I just have. So there it is, 30 pounds, and then we're going to go across from our line on our graph, and that works out at 40 euros. So the next question then says, use the graph to change 16 euros to pounds. This time we're starting on the euros side, so we're converting 16 euros into pounds. So we need to find out where 16 is. So each little box is worth 1 because there's 10 little sections between 0 and the number 10. So that means each box is worth €1. So to find 16, that will be 15, and 1 above 15 there's your 16. So let's zoom in here so we get a nice accurate line. So we're drawing along that line. Oh, we just went past it there a little bit. Try that again. So there we've met the line. There we're going to draw down. Okay, and again, similarly on this bottom scale for the pounds, each is worth £1. So that's 10, 11, 12. So that means that 16 euros is worth £12. Okay, we've got one more conversion graph to look at. Maybe you want to take now time and pause the video and try this yourself, and then you can come back and check if you have got the same answers as me, if you got them right. So this conversion graph can be used to change between meters and feet. Use the conversion graph to change 6 metres to feet. So metres is on our bottom scale and we want to change 6 metres into feet. So I'm going to draw up here. Again, we can zoom in just to make sure we're nice and accurate. So 6, going to draw straight up to where you meet the line and then across. So that is telling us that 6 metres is equivalent to 20 feet. So 6 metres is 20 feet. Then it says in B, use the conversion graph to change 8 feet to metres. So we need to find 8 feet here. So let's go to our feet. There we are, there's our feet. I'm going to find 8, so that's 5, 6, 7, 8. I'm going to just zoom in again. And I'm going to draw across at 8. Okay, do we meet the line? Then I'm going to come down. Now we need to work out what the scale is going up in. So if this is 2, that's not 1 and then 2. But so that means that between here 2, we've gone to 3. So it's 2 point something. So that would be 1, 2, 3, 4, 5. So we're dividing 1 into 5. So that means each of these is 0.2. So that's 2.1 or 2.2 and then 2.4. So 8 feet is 2.4 metres. Okay, next question. Robert jumps 4 metres. James jumps 12 feet. Who jumps furthest? James or Robert? So we need to convert these, one of them. So either they're both in metres or they're both in feet. So we'll look at our 4 metres. Let's take our 4 metres. So we're going to convert Robert's into feet. So let's go back up to our graph. And it says Robert jumped 4 metres. So here's our metres. And there's 4. So I'm going to just draw my line up there. And then I'm going to go across. It comes out there. So that's 10, 11, 12, 13. So if we go back down to the question, that means that 4 metres is the equivalent to 13 feet. So it says, who jumped furthest, Robert or James? Well, Robert, he jumped 13 feet and James jumped 12 feet. So in fact, it was Robert who jumped the furthest. Now, if you go on to the next part, it says, how did you get your answer? So basically, you're going to explain what you did. You converted your 4 metres using your graph to 13 feet. And that told you that Robert had jumped further because he had jumped 13 feet. Hope you find this helpful. And if you have any questions, you can put that into the wee comment section and I will try and answer them for you.